Download this code from codegive.com, link in the description below. OK, let's dive deep into compiler design with a focus on source language issues. This will be a comprehensive guide covering various aspects, challenges, and examples to help you understand the complexities involved. Table of Contents *. 1. Introduction to compiler design. *1.1 What is a compiler? *1.2 The compilation process, phases. *1.3 Source language considerations. 2. Lexical analysis, scanning. *2.1 Role of the lexical analyzer. *2.2 Tokens, lexemes, and patterns. *2.3 Regular expressions and finite automata. *2.4 Source language impact, keywords, identifiers, literals. *2.5 Code example, lexer in Python. 3. Syntax analysis, parsing. *3.1 Role of the parser. *3.2 Context-free grammars, cfgs. *3.3 Parse trees and abstract syntax trees, asts. *3.4 Parsing techniques, top-down, ll, bottom-up, lr. *3.5 Source language impact, ambiguity, operator precedence, associativity. *3.6 Code example, simple parser in Python. 4. Semantic analysis. *4.1 Role of the semantic analyzer. *4.2 Type checking, static versus dynamic. *4.3 Symbol tables. *4.4 Scope resolution. *4.5 Source language impact, type systems, data structures, object orientation. *4.6 Code example, basic type checking in Python. 5. Intermediate code generation. *5.1 Purpose of intermediate representation, IR. *5.2 Common IR forms, 3. Address code, abstract syntax trees. *5.3 Source language impact, high-level features, control flow. *5.4 Code example, generating 3 address code. 6. Code optimization. *6.1 Goals of optimization. *6.2 Common optimization techniques, constant folding, dead code elimination, loop optimization. *6.3 Source language impact, optimization opportunities, language-specific idioms. 7. Code generation. *7.1 Target machine architecture. *7.2 Register allocation. *7.3 Instruction selection. *7.4 Source language impact, calling conventions, memory management. 8. Source language issues in depth. *8.1 Static versus dynamic typing. *8.2 Memory management, garbage collection, manual. *8.3 Exception handling. *8.4 Concurrency and parallelism. *8.5 Reflection and metaprogramming. 9. Conclusion. 1. Introduction to compiler design. *1.1 What is a compiler? A compiler is a computer program that translates source code written in a source language into equivalent code in a target language. The target language is often machine code for a specific processor, but it can also be another high-level language, example compiling TypeScript to JavaScript. The primary goal of a compiler is to produce functionally equivalent code that can be executed by a machine or another interpreter. *1.2 The compilation process, phases. A typical compiler is structured into several phases, each performing a specific task. 1. Lexical analysis. Scanning breaks the source code into a stream of tokens, keywords, identifiers, operators, etc. 2. Syntax analysis. Parsing constructs a parse tree or abstract syntax tree, AST, based on the grammar of the language. 3. Semantic analysis. Asterisk checks the meaning of the code, including type checking, scope resolution, and ensuring that the code adheres to the language's rules. 4. Intermediate code generation. Asterisk transforms the AST into an intermediate representation, IR, which is a machine-independent representation suitable for optimization. 5. Code optimization. Asterisk improves the IR to produce more efficient code. 6. Code generation. Asterisk translates the optimized IR into the target machine code. Asterisk 1.3 Source language considerations. The design and implementation of a compiler are heavily influenced by the characteristics of the source language. These considerations include grammar and syntax. The language's syntax determines how code is structured and how the parser will interpret it. Ambiguities in the grammar can create challenges. Type system. Static versus dynamic typing significantly impacts semantic analysis and code generation. Memory management. Whether the language uses garbage collection or manual memory management affects the compiler's code generation strategies. Features. Features like object orientation, concurrency, and exception handling add complexity to the compilation process. 2. Lexical analysis, scanning. 2.1 Role of the lexical analyzer. The lexical analyzer, also known as a scanner, is the first phase of the compiler. Its main task is to read the source code character by character and group them into meaningful units called tokens. It eliminates witty space and comments. 2.2 Tokens, lexemes, and patterns. Token. A category representing a type of element in the source code, example identifier, integer underscore literal, plus, keyword. Lexeme. The actual sequence of characters that matches a token's pattern, example x, 123, plus, if. Pattern. A description of the form that the lexemes of a token can take. Often expressed as a regular expression. 2.3 Regular expressions and finite automata. Regular expressions are a powerful way to define the patterns for tokens. The lexical analyzer often uses finite automata, DFAs and NFAs, to efficiently recognize these patterns. Example regular expressions AZAZ underscore AZAZ 0-9 underscore asterisk, identifier. 0 to 9 plus, integer literal. Plus operator. 2.4 Source language impact, keywords, identifiers, literals. The source language dictates the set of keywords, the rules for identifier naming, and the types of literals allowed. The lexical analyzer must be configured to recognize these language-specific elements. Keywords. Reserved words with special meaning, example if, else, while, for, class. The lexer must correctly identify these keywords. Identifiers. Names given to variables, functions, classes, etc. The language specifies the allowed characters and naming conventions. Literals. Constant values, example integers, floating point numbers, strings, booleans. The lexer must convert these literals into their internal representations. 2.5 Code example, lexer in Python. This Python code implements a simple lexical analyzer. It iterates through the source code, identifying tokens such as integers, identifiers, operators, and keywords. The tokenize method returns a list of token objects, each representing a recognized token. 3. Syntax analysis, parsing. Asterisk 3.1 Role of the parser. The parser takes the stream of tokens produced by the lexical analyzer and constructs a syntax tree or abstract syntax tree, AST, representing the grammatical structure of the code. It verifies that the code conforms to the language's grammar. Asterisk 3.2 Context-free grammars, CFGs. Context-free grammars are used to formally define the syntax of a programming language. A CFG consists of asterisk terminals asterisk the tokens produced by the lexical analyzer. Asterisk non-terminals asterisk symbols representing syntactic categories, example expression, statement, program. Asterisk production rules asterisk rules that define how non-terminals can be expanded into sequences of terminals and non-terminals. Asterisk start symbol asterisk a special non-terminal that represents the entire program. Asterisk example CFG asterisk. Asterisk 3.3 Parse trees and abstract syntax trees, ASTs. Asterisk parse tree asterisk a tree-like representation of the grammatical structure of the code, showing how the tokens are derived from the grammar's production rules. It reflects the complete syntactic structure. Asterisk abstract syntax tree, AST a simplified representation of the parse tree, omitting unnecessary details, example punctuation, intermediate non-terminals. The AST focuses on the essential semantic structure. Asterisk 3.4 Parsing techniques, top-down, LL, bottom-up, LR. Asterisk top-down parsing, LL starts from the root of the parse tree, the start symbol, and attempts to derive the input string by expanding non-terminals. Examples, recursive descent parsing. LL parsers are easier to understand and implement manually. LL, K, parsers can look ahead K tokens to make parsing decisions. Asterisk bottom-up parsing, LR starts from the input tokens and attempts to reduce them to the start symbol. Examples, shift-reduce parsing, LR, SLR, LALR, and parser generators like yak/bison. LR parsers are more powerful and can handle a wider range of grammars. Asterisk 3.5 Source language impact, ambiguity, operator precedence, associativity. Asterisk ambiguity asterisk a grammar is ambiguous if there exists at least one string that can be derived by multiple parse trees. Ambiguity can lead to incorrect interpretations of the code. Asterisk operator precedence asterisk the order in which operators are evaluated, example multiplication before addition. The grammar must be designed to enforce the correct precedence. Asterisk associativity asterisk determines how operators of the same precedence are grouped, example left to right associativity for subtraction, A, B, C is interpreted as A, B, C. Asterisk 3.6 Code example, simple parser in Python. This Python code demonstrates a simple recursive descent parser that can parse arithmetic expressions. It builds an abstract syntax tree, AST, to represent the structure of the expression. The parse method initiates the parsing process, and the expression, term, and factor methods correspond to the grammar rules. The AST is represented as nested tuples. 4. Semantic analysis. Asterisk 4.1 Role of the semantic analyzer. The semantic analyzer checks the meaning and consistency of the code, ensuring that it adheres to the language's semantic rules. This phase catches errors that cannot be detected during lexical or syntactic analysis. Asterisk 4.2 Type checking, static versus dynamic. Asterisk static typing asterisk type checking is performed at compile time. The compiler verifies that the types of variables and expressions are consistent. Examples: C++, Java, Rust. Dynamic typing type checking is performed at runtime. The type of a variable is not known until the program is executed. Examples: Python, JavaScript, Ruby. 4.3 Symbol tables. A symbol table is a data structure used to store information about identifiers, variables, functions, classes, etc. The semantic analyzer uses the symbol table to store type information, track the scope of variables, detect undeclared variables or duplicate declarations. 4.4 Scope resolution. Determining which declaration a particular use of a variable refers to. This involves following scoping rules, example lexical scoping, block scoping. 4.5 Source language impact, type systems, data structures, object orientation. Type systems the language's type system, example strong versus weak typing, static versus dynamic typing, greatly affects the complexity of semantic analysis. Data structures the semantic analyzer needs to understand the language's data structures, example arrays, structs, objects. Object orientation object-oriented features, example classes, inheritance, polymorphism, require more sophisticated semantic analysis. For example, checking method overriding rules or resolving virtual function calls. 4.6 Code example, basic type checking in Python. This code implements a rudimentary semantic analyzer that performs type checking for assignments and arithmetic operations. It uses a symbol table to store the types of variables. The analyze method traverses the AST, visiting each node and performing type checks. If a type error is detected, an exception is raised. 5. Intermediate code generation. 5.1 Purpose of intermediate representation, IR. The intermediate representation, IR, is a machine-independent representation of the source code. It serves as a bridge between the front-end, lexical analysis, syntax analysis, semantic analysis, and the back-end, code optimization, code generation. Using an IR simplifies the compiler design by allowing the front-end and back-end to be developed independently. 5.2 Common IR forms, 3 Address code, abstract syntax trees. 3 Address code, TAC a sequence of instructions where each instruction has at most 3 operands. TAC is often used as a low-level IR. Example. Abstract syntax trees, ASTs can also serve as an IR, especially for languages with complex features. The AST can be annotated with type information and other semantic attributes. 5.3 Source language impact, high-level features, control flow. High-level features features like object orientation and exception handling require special IR constructs to represent them. Control flow statements, example if, while, for, need to be translated into IR that represents the control flow graph. 5.4 Code example, generating 3 address code. This code implements a simple TAC generator. The generate_code method takes the AST as input and produces a list of TAC instructions. The generate method recursively traverses the AST, generating TAC for each node. Temporary variables are introduced to store intermediate results. 6. Code optimization. 6.1 Goals of optimization. The primary goals of code optimization are to Asterisk reduce the execution time of the code. Asterisk reduce the size of the code. Asterisk reduce power consumption, for embedded systems. Asterisk 6.2 Common optimization techniques. Asterisk constant folding. Asterisk evaluating constant expressions at compile time. Asterisk dead code elimination. Asterisk removing code that is never executed or whose results are not used. Asterisk loop optimization. Asterisk techniques like loop unrolling, loop invariant code motion, and strength reduction. Asterisk common sub-expression elimination. Asterisk identifying and eliminating redundant calculations. Asterisk inlining. Asterisk replacing function calls with the function's body. Asterisk 6.3 Source language impact, optimization opportunities, language-specific idioms. The opportunities for optimization depend on the characteristics of the source language and the coding style used by programmers. Language-specific idioms can be exploited to improve performance. Asterisk example. Asterisk in some languages, string concatenation can be optimized by using string builders instead of repeated string additions. 7. Code generation. Asterisk 7.1 Target machine architecture. The code generator must be aware of the target machine's architecture, including asterisk instruction set, asterisk registers, asterisk memory organization, asterisk calling conventions, asterisk 7.2 register allocation, assigning variables to registers to reduce memory accesses. Register allocation is a complex optimization problem. Asterisk 7.3 Instruction selection. Choosing the appropriate machine instructions to implement the IR. This involves considering the cost and performance of different instruction sequences. Asterisk 7.4 Source language impact, calling conventions, memory management. Asterisk calling conventions. Asterisk the conventions for passing arguments to functions and returning values. Asterisk memory management. Asterisk if the language uses garbage collection, the code generator needs to insert code to trigger garbage collection. 8. Source language issues in depth. Asterisk 8.1 Static versus dynamic typing. Asterisk static typing. Asterisk advantages. Asterisk early error detection, improved performance, less runtime type checking, better code maintainability. Asterisk challenges. Asterisk requires more complex type systems, example generics, type inference, can limit flexibility. Asterisk dynamic typing. Asterisk advantages. Asterisk more flexible and concise code, faster development cycle. Asterisk challenges. Asterisk runtime type errors, potential performance overhead, harder to debug and maintain. Asterisk 8.2 Memory management, garbage collection, manual. Asterisk garbage collection, GC automatic memory management. The runtime system automatically reclaims memory that is no longer in use. Asterisk advantages. Asterisk reduces memory leaks, simplifies programming. Asterisk challenges. Asterisk performance overhead, unpredictable pauses. Different GC algorithms have different trade-offs. Asterisk manual memory management. Asterisk the programmer is responsible for allocating and freeing memory. Asterisk advantages. Asterisk more control over memory usage, potentially better performance. Asterisk challenges. Asterisk prone to memory leaks, dangling pointers, and other memory-related errors. Asterisk 8.3 Exception handling. The compiler must generate code to handle exceptions, runtime errors. This involves asterisk creating exception tables to track exception handlers. Asterisk generating code to unwind the stack when an exception is thrown. Asterisk ensuring that resources are properly cleaned up in the presence of exceptions. Asterisk 8.4 Concurrency and parallelism. Source languages that support concurrency and parallelism require the compiler to generate code to manage threads or processes. Implement synchronization mechanisms, example locks, semaphores. Optimize code for parallel execution. 8.5 Reflection and metaprogramming. Reflection the ability of a program to examine and modify its own structure and behavior at runtime. Metaprogramming writing code that manipulates other code, example generating code at compile time. These features require the compiler to generate code that provides access to runtime type information and code generation capabilities. 9. Conclusion. Compiler design is a complex and challenging field, but it is also essential for modern software development. The design of a compiler is heavily influenced by the source language. The choices made in the source language design have a direct impact on the complexity of the compiler and the performance of the generated code. Understanding the issues related to source language features is crucial for building efficient and reliable compilers. This tutorial has provided a comprehensive overview of compiler design, focusing on the impact of source language issues. It covered the various phases of compilation, common challenges, and examples to illustrate the concepts. Good luck in your compiler design endeavors.